Good afternoon, students. Am I audible? Am I audible?
Yes, sir.
Yes, sir.
Okay. So what were we discussing in yesterday's class? I think we were discussing some terms, right, related to magnetic properties of a material. So in today's class, we will see about the different types of magnetism. I would have told you yesterday, right? So what are the types of magnetism that are there? Paramagnetism, diamagnetism, and
Paramagnetic, diamagnetic, and
ferromagnetic and diamagnetic, right? So before we start discussing what those materials are, let's have a look at a small video. Okay. See, the thing, I think the sound might not be audible to you guys, so I'll be explaining. I want you all to observe the activity clearly. Okay.
You might not think of water as being magnetic.
See, he has a magnet and the right side one is a magnet. Okay. With that, what he is doing is taking it close to water. So what do we expect? Let's see.
But it is.
Did you observe what happened?
You might not think of water as being magnetic, but it is. And so are graphite, aluminum, and glass.
Did you observe what happened to water? When the magnet was taken close to the water sample, what happened to it?
Repelled.
It repelled, no? Okay. So we'll see what is the reason for it.
This is a new and different category of magnetism called either para or diamagnetism, and it's different from the magnetism that you're used to. You're probably already
So we discussed something yesterday, right? You have an iron nail, a very big nail is there, and there are some pins which are there. There are some clip pins, right? So he will try to take that iron nail and try to attract them. Obviously, what do you think will happen? Will that iron nail be able to attract those pins or clips?
No,
Will it happen? Guys, are you there? I'm asking, will that nail be able to attract those pins? Is what I'm asking.
no, sir.
No, right? Why is it not going to happen? Because there is no magnetism induced in that iron nail. But see what will happen now.
familiar with ferromagnetism. Ferro means iron. An unmagnetized piece of iron, or nickel, or cobalt, becomes a magnet in the presence of a magnetic field.
So it was an instant process, right? As soon as the iron nail was attached to the magnet, it started attracting the clips, right? Why did this happen? It is because the dipoles inside that iron nail got arranged in such a way that there is a magnetism induced in it. Accepted? Right?
Yes, sir.
The effect is strong and lasts even
After the magnet is removed also, the iron nail is able to still hold those clips. There, it is still able to attract those materials. Why is it happening? It is because the iron nail is able to retain the magnetism that is given to it. Okay, remember, there is an important theory we are going to discuss about this property for a ferromagnetic substance. So this property is called as retention of magnetism.
is removed. Paramagnetism is a similar effect, except that it's much
So he has some
temporary.
paramagnetic substances. Observe how they are going to respond to the external magnetic field.
Aluminum is a good example of a paramagnet.
So what happened? Was it getting attracted or repelled?
getting attracted, sir.
Attracted, right? Because it is trying to come towards the magnet. So aluminum is an example of a paramagnetic substance. We don't call it as ferromagnetic because paramagnetic substance tend to show some attractive behavior just similar to ferromagnetic materials, except the fact that ferromagnetic substances are more inclined, they are more susceptible to get magnetized compared to a paramagnetic substance. Okay, so what I'm trying to say is paramagnetic substance and ferromagnetic substance have a similar behavior, except the fact that paramagnetic effect is feeble, ferromagnetic effect is very strong.
And so is oxygen, which is attracted to magnets. Here, I have a few milliliters
So
of
this is a
liquid
liquid oxygen,
which sticks
it
to
is
the
getting
magnet.
attracted.
I'll explain why later. Gadolinium oxide and cupric sulfate are good examples of paramagnetic substances. Cupric sulfate is a salt that can be picked up by a magnet.
So did you understand what happened? So paramagnetic substances also will get attracted, but it is a feeble attraction. Then what is going to be the scenario with respect to a diamagnetic substance? Let's see. So now you guys tell me, is water a paramagnetic substance or a diamagnetic substance? You saw something in the beginning, right? Beginning of this video, water was there. Did water repel the magnetic field or attract towards the magnetic field? Guys, initially in the video, I showed you something, right? Water, did it get attracted or repelled?
Repelled, sir.
It repelled, no? So those kind of materials are called as diamagnetic materials.
Diamagnetic materials are exactly the opposite of paramagnetic. They are always repulsed. They would rather die than be in a magnetic field. An important example of a diamagnetic material is graphite. This specially made pyrolytic graphite is repelled by a magnetic field. Don't be confused. This is not static electricity or eddy currents. Graphite is repelled by a magnet, always, both by the north and south end.
Did you understand?
Pyrolytic graphite is a grown crystal of flat carbon layers which maximizes the diamagnetic effect. Of course, the best diamagnets are superconductors, which at low temperatures provide exact opposite repulsion to whatever magnetic field is present.
So that is an example of magnetic levitation. Okay.
They are perfect diamagnets. The most famous and powerful diamagnetic is bismuth, element number 83 on the periodic table. The bismuth-powered boat sails toward the weaker magnetic fields.
Okay. Now tell me one thing. What do you think is the reason for paramagnetism or diamagnetism to occur in a material? So on an atomic level, what do you think is the reason for paramagnetic substance or a diamagnetism to get erased? You can at least guess.
So due to the number of
Sorry, due to?
number of electrons.
Okay.
present in a
Okay, number of electrons. Okay, accepted. It's almost there, but one more point is needed. So when you write the electronic configuration along with their spin, you can talk about paired electrons and unpaired electrons, right? So if you have a particular element where you have paired electrons, those materials act as diamagnetic substances. For example, if you take water, so how is water written? So on hydrogen, on oxygen, you have two lone pairs of electrons, right? These electrons are paired and these electrons are also paired. So these kind of materials exhibit diamagnetism. So materials which have paired electrons exhibit diamagnetism. For example, if you take aluminum, the atomic number is 13, right? So what is going to be the electronic configuration? 2, 8, and 3, right? So in this, you will have 2 electrons which are paired and 1 electron which is unpaired. So that is the reason why aluminum is said to have a paramagnetic behavior. Okay, so diamagnetism is exhibited by materials which have all electrons paired. Even if there is one unpaired electron, then it is going to exhibit paramagnetism. Okay, so that is the reason. Now we will see how those paramagnetic and diamagnetic substances will respond to a strong magnetic field when they are suspended. Okay, see.
Check whether an object is diamagnetic or paramagnetic is to see how it aligns itself in a magnetic field. Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic.
Glass is there, right? There is a magnetic substance brought. Initially, the glass was horizontal, like I would say it was along the x-axis, right? Now, because of the magnet also, there is a magnetic field along the x-axis, right? But what is happening to glass? You look at the way the glass is getting aligned. Check, no?
Diamagnetic objects like glass will rotate to avoid magnets. Here, we see that the glass is diamagnetic because it twists to get to the weaker magnetic
So what did
field.
glass do? It was trying to align itself in the direction of weaker magnetic field. So this is the kind of behavior exhibited by a diamagnetic substance. Whereas if you suspend an aluminum rod of that size, see what will happen.
But aluminum rotates into the field, typical of a
What happened?
paramagnet.
It tried to align itself along the direction of the magnetic field. So paramagnetic substances get aligned in the direction of strong magnetic fields, whereas diamagnetic substances align themselves in the direction of weaker magnetic field. Am I clear with this, guys?
Yes, sir.
Yes, sir.
On the periodic table, we see that aluminum has 3 valence electrons. So what does it take to understand what it means for something to be a paramagnet or a diamagnet? You have to know what the electrons are doing. Consider, for example, aluminum. We see from the periodic table that aluminum has 3 valence electrons. That's 2s and 1p.
So it has an unpaired electron.
Now it's that unpaired electron that makes it a paramagnet. This unpaired electron enables it to become magnetized. And it's that unpaired electron that is free to be magnetized and attracted by the magnet. But what about a diamagnet, like water? Yes, the water molecule. It has all of its electrons paired. It will not be magnetized. In fact, water is repelled by a magnetic field. The electrons
Here,
come
guys.
to lower energy as they are moved away from the
So
magnet.
this is the theory on the basis of which we are going to do a comparative study of the properties of dia, para, and ferromagnetic substances. Okay. First, the effect of magnets. So when a diamagnetic substance is taken close to a magnet, how will it behave? Will it attract or repel? It is obviously going to repel, right? So when you talk about repulsion, is it going to be a strong repulsion or a feeble repulsion? It is a feeble repulsion, like how water repelled, right? So it's feebly repelled by the magnets, whereas paramagnetic substance also have attraction, but it is a feeble attraction. Whereas the ferromagnetic substances, they are strongly attracted by the magnets. Am I clear? So that is in the presence of permanent magnets. The second scenario is when you place a diamagnetic substance in external magnetic field, what will happen to it? So they acquire feeble magnetization in the opposite direction of the magnetizing field. Means If the magnetizing field is in the rightward direction, then the diamagnetic substance will obtain the magnetization in the opposite direction. Okay. Next. What about a paramagnetic substance? It acquires feeble magnetization in the direction of magnetizing field. Okay. Whereas a ferromagnetic substance will also acquire magnetization, but this time it is going to be strong in the direction of magnetizing field. So what I'm trying to say is para and ferro will have similar kind of a behavior except feeble and strong. Okay. Next. In the presence of a non-uniform electric field, like how you saw that experiment, right? There was a glass rod that was suspended and the glass rod tried to align itself in the direction perpendicular to the existing magnetic field, right? So whenever you subtend a diamagnetic substance, the presence of a non-uniform magnetic field, it tends to move slowly from a stronger to weaker parts of the field. Whereas when you talk about a paramagnetic substance, tend to move slowly from weaker to stronger parts of the field, and ferromagnetic substance tend to move quickly from weaker to strong magnetic fields. Okay, next. What happens in the presence of a uniform magnetic field? Okay, so when it was non-uniform, when it was trying to align itself in the direction perpendicular to the magnetic field, when it is uniform, what will have, sorry, when it was trying to align in the non-uniform magnetic field, when a diamagnetic substance was trying to align itself in the direction of weaker magnetic fields, in the presence of uniform magnetic field, it will align itself in the direction perpendicular to the field. Okay. Whereas a paramagnetic substance will align itself parallel to the field. You can remember like this: parallel, P-A-R-A. The first four letters of parallel is para. So you can remember it like that. They'll get aligned in the direction parallel to the field. Then what about a ferromagnetic substance? A freely suspended ferromagnetic rod aligns itself parallel to the field. Okay, when paramagnetic is parallel, ferro will also be parallel. Am I clear till this point?
Yes, sir.
Good. Next is, what about the susceptibility? Means the extent to which you can magnetize a diamagnetic material. The susceptibility of a diamagnetic substance is negative, means you cannot magnetize it, but it's very less. So susceptibility is small and negative, which is generally between -1 to 0. Whereas for a paramagnetic substance, susceptibility is a small and a positive number, which is somewhere between 0 to epsilon, where epsilon is a small number, some variable, that's it. It is going to be a small number. Whereas when you look at the susceptibility of iron, it is very much greater. It is greater than 1000. Means it will get magnetized that fast. Okay. Next. Relative permeability. I hope you guys remember this. Relative permeability is permeability divided by the permeability of free space. Relative permeability is slightly less than 1. Here it is slightly greater than 1. And here it is of the order of few thousands. Okay. Next. What about the permeability? So here the permeability of the material is less than mu naught. That is why the value is between 0 to 1. Here the value of permeability is greater than mu naught. That is why it is greater than 1 and lesser than a smaller number. Here it is very much greater than the permeability of free space. Okay. Shall I proceed?
So could you repeat this point again?
Okay. See. Relative permeability is mu divided by mu naught.
Yes, sir.
So in this place, if I substitute 0 less than or equal to mu divided by mu naught is less than 1. If I take this inequality, can I say mu is less than mu naught?
Yes, sir.
Similarly, if I substitute it here, mu divided by mu naught is less than 1 plus some small number and it is greater than 1. So if I take this inequality, can I say mu is greater than mu naught?
Yes, sir.
In a similar way, here mu divided by mu naught is very much greater than 1000. So mu will be greater than, mu will be very much greater than mu naught, because mu is 1000 times more than mu naught. So that is why it is written as very much greater than mu naught. Where mu naught is the permeability of free space and mu is the permeability of the magnetic substance. Is that clear? Now see, effect of temperature. So diamagnetic substances, the susceptibility of diamagnetic substance is independent of temperature. Okay, anyways, the material is not going to get magnetized. So what is the point? Whereas in the case of a paramagnetic substance, susceptibility varies inversely as temperature. Means if you take a paramagnetic substance and start increasing its temperature, the extent to which it can get magnetized will decrease. So susceptibility is inversely proportional to temperature. Whereas when you talk about the when you talk about a ferromagnetic substance, then we can say susceptibility decreases with temperature in this manner. Susceptibility is inversely proportional to T minus Tc, where Tc stands for Curie's temperature. Okay. So here Curie's temperature means the temperature at which a ferromagnetic substance will completely lose its magnetic property. I repeat. So Curie's temperature is the temperature at which a ferromagnetic substance will lose its magnetism completely. So I hope you guys made a note of this point. This is very, very important point, guys. So susceptibility is inversely proportional to temperature in the case of paramagnetic. In the case of ferromagnetic, it is inversely proportional to T minus Tc. Okay. Ninth one. Removal of magnetizing field. So when you remove the magnetizing field, a diamagnetic substance will get demagnetized immediately. A paramagnetic substance will lose its magnetism immediately, whereas a ferromagnetic substance can retain its magnetic property. And this principle is what is called as, or I can say this characteristic is what is called as retention. If you guys remember, even after the magnet was removed, the nails were able to hold those iron particles. You remember? So that's what we call it as retention. What is retention and technical definition? We will see it in the next topic. Yes, sorry, I had some network issue. So what was the last topic we were discussing? It was about the removal of magnetizing field, right?
Yes, sir.
Yeah. So when you remove the magnetizing field, what will happen? Diamagnetic substance will lose its magnetism. Right? Then as soon as for a paramagnetic substance also the same thing, and for a ferromagnetic substance it will be able to retain the magnetism, and that's what is called as retention. I told you, right? Retention. What is retention? We will see it in the subsequent topic. Next is variation of M and H. What does M stand for? M stands for anybody? M stands for intensity of magnetization, and H stands for magnetizing field intensity. Right? So, in the case of a paramagnet, in the case of a diamagnetic substance, M changes linearly with H. Means as H is increasing, M will also increase linearly. Whereas in the case of a paramagnetic substance, M will change linearly with H, but there is one important thing. It will attain saturation at low temperature and in the presence of very strong fields. The meaning of saturation is, as you keep increasing the magnetizing field intensity, the material will no more get magnetized because it has got magnetized to the maximum possible extent. Okay. Then what about a ferromagnetic substance? M changes with H non-linearly and ultimately attains saturation. Okay. M changes with H non-linearly and ultimately attains saturation. Okay. Next. This
So I have a
hysteresis.
doubt.
Please tell me.
So for 10th one, we can say in paramagnetic substances, H will not increase anymore, sir, after saturation. H will not increase anymore after saturation point.
No. H is input. Means you've got confused. See. Iron bar, iron nail. H is the input, M is the output. Okay. You keep giving magnetizing field intensity, the extent to which the material will get magnetized will increase. Means if you give 1 unit of this, then you can see 1 unit of something here, or let's say X unit here. Then if you increase it to 2 units, here you will be able to see 2x units. If you increase it to 3 units, you will see 3x units. You're able to understand?
Yes,
So like
understood.
increasing, let's say at 5 units, here you are able to see 5x. At 6 unit also, if you are able to see 5x, then you can say that the material has got saturated. The magnetization has got saturated. That is the meaning.
Okay, sir, I understood.
Okay. Yes. Whereas in the case of ferromagnetic substance, what will happen is M and H are not linearly proportional. They are non-linearly proportional. Okay. So this hysteresis effect is a very, very important thing, which I will explain next. So I'm not discussing at this point. The next is, what about the physical state of the materials? If you talk about a diamagnetic substance, the physical state can either be solid, liquid, or gas. Similar is the case with respect to a paramagnetic also, whereas with respect to ferromagnetic substances, they are generally solids. Because you say ferro is related to iron. Mostly they are iron substances. Okay. There are certain examples given, which you guys can read it later. You can just take a screenshot. These are all the examples of dia, para, and ferromagnetic substances. Okay. Now, I want to explain about hysteresis effect. Okay. Let me explain it. Please. Write down the heading, guys. hysteresis effect, or sometimes we call it as hysteresis loop also, because it has a graph associated with it. Okay. Now I want you guys to revisit the definitions we discussed yesterday and tell me what is the mathematical definition of permeability. So what is the mathematical definition of permeability? Mu is equal to
ratio of magnetic induction to magnetic field intensity.
very good. It is B divided by H, which implies B is equal to mu into H. Accepted? Okay. Now I have a question. So B is magnetic induction. H is magnetizing field intensity. Correct? So here in this expression, which is the input quantity and which is the output quantity?
So B is input, sir.
B is input. B is input or output? The magnetic induction, is it getting generated, or is it an effect which is making the material get magnetized? Out of B and H, which is needed for the material to get magnetized?
B is needed, sir.
B is needed. B is the output. Only if you give magnetizing field intensity, the material can get magnetized. There is reason why I'm asking. So what I'm asking is, if you give H, will you be able to see B? Or if you give B, you will be able to see H. What is needed to be given as input? H should be given. That
H
is
is
a
input, sir.
magnetizing field intensity should be given so that you are able to observe the magnetic induction taking place. Right? When this is the scenario, then we know the fact that, see, whenever you have a graph, 2x plus 3y is equal to 5. So y is equal to 5 minus 2x divided by 3, right? So if I ask you to plot a graph for this relation, what will you do? You will take the independent values and put it in the place of x. That is, whichever value you want to choose, you will substitute in the place of x, and you will get a dependent value y, right? So whenever graph is drawn, you need to ensure that the x-axis is independent and y-axis is dependent. Did you understand why I asked? Means H should be taken on the x-axis and B should be taken on the y-axis. Means have this in your mind. If you keep giving H, B will get generated. But let's say you're giving the value of H as 1 unit, and do you think, let's say B is coming out as X units. Okay. If you increase the value of H to 2 units, what do you think B will be?
2x units, sir.
We will expect it to be 2x units, no, but this will not be the scenario in the case of a ferromagnetic substance, because the material has a very high value of susceptibility. I repeat, ferromagnetic substances have very high value of susceptibility that they can get magnetized very fast. Meaning, as you keep increasing the value of H, even a smaller value of H given to it can bring in a lot of change in the value of B. So the graph, if you observe, this is not looking like the form y is equal to mx. So what is y is equal to mx supposed to be? It should have been a straight line passing through the origin. Y is equal to mx should have been a straight line passing through the origin, but it will not be a straight line passing through origin. Rather, the curve will be like this. Means even for lesser value of H, you can observe more value of B getting generated, and the graph will increase till a particular value where it will get saturated. And this value is called as H max. So as you keep increasing the value of H, the value of D will get increased and then it will get saturated. Means beyond this H max, what will happen is the material will no more get magnetized because it has attained maximum magnetization possible. You're able to understand this?
Yes, sir.
So between 0 to H max, this is what is happening. So I will write it like this. 0 to H max, what happened? Graph is curved. Okay. Now, if H is completely removed. So what is the meaning of completely removed? If H is completely removed means, let's say, okay, and you placed it in the presence of an external magnet like this, then you keep, okay, let's do it like this. You have a rod like this around which there is a coil. Okay, you kept increasing the value of the potential difference so that you increase the current. When the current is increased, the magnetizing field intensity will increase because you remember B is equal to B naught is equal to mu naught into Ni. This Ni is what is written as H. So you guys remember this. So as I increases, H will keep increasing. Then what will happen is this material which is inside will get magnetized more. Yes or no? So when it is getting magnetized, there will be a particular saturation value beyond which you cannot magnetize that material. It has attained this highest property. Now let's say this particular system has a switch. Okay. Now what if the switch is opened? All of a sudden you open the switch, then the value of current is going to be 0. When current is 0, can I say that the magnetizing field intensity is also 0? Right.
Yes, sir.
Then what is supposed to happen? We expect the material to lose its magnetism. Means when you do this experiment, what will be your expectation? See, let's say you're doing this for the first time. In today's world, yes, we know that that iron will be able to retain all those things. But initially, when you did this experiment, what will you see? You will see that that iron is still able to exhibit magnetism even on the removal of external magnetic field. But what will happen? It will slightly keep losing its property, but not very fast. It will slightly lose its magnetism, right? And what do we expect? We expect that it will lose its magnetic property exactly in the path in which it has attained, right? So this is the path in which it has attained magnetism. Now my question is, if I call this point as A, will it get demagnetized because of the removal of external magnetic field exactly in the direction of AO? Guys, think about it. Is it going to get demagnetized exactly in the direction AO itself? From O to A, it got increased. Is it going to decrease from A to O? Is that what is going to happen? The answer is no. Rather, the material will lose its magnetism in this direction. Okay. And if I call this point as, let me see. And let me call this point as P. Because I've used B here, I don't want to use that again. Let me call this point as P. Then, what does this part of the graph tell us? What does this part of the graph tell us? If I take the coordinates of this point, it will be how much? 0, OP. Correct? 0, OP. Where OP is the distance along the y direction. right? But OP corresponds to the value of Y. Y stands for what? Magnetic induction. So looking at this coordinate, can I say, even when there is a zero magnetizing field present in the material, I repeat, even when there is a zero magnetizing field present, can I say that the material is able to retain the magnetism? Yes or no? Then the distance OP is what is called as retentivity. It's called as retentivity. Am I clear with this?
Yes, sir.
Right. So what is the definition of retentivity? I'll explain it. But as of now, have the word retentivity in your mind. Okay. Now what I'm going to do is, I'm going to reverse the direction of H by changing the polarities. I'm going to reverse the direction of H, okay, in such a way. I'm going to reverse the direction of H in such a way that initially, when I went from O to A, the material had zero magnetization in it. Correct? Zero magnetic induction in it. So it was H that was helping the material to get magnetized. Till where? Till the point A. Right? Now I have a question. When you start applying H at O in the reverse direction, what will happen? The material is already having magnetic property, unlike the previous case where it started from O, that first you need to demagnetize the material, right? Means you need to first make the material get demagnetized, let's say at this point Q. After that, what will happen is, from here, it will go as if it went in the direction of A, from direction O to A. So this point will be R. And here it will attain saturation in the reverse direction. This I will call it as minus H max. Rather, I can call this as B max rather than calling it as H max. I'll call this as B max. I'll call this as minus B max. Are you guys able to understand this point? So it is going to attain saturation in this direction. After attaining the saturation, if you remove the magnetic field again, what will happen? It will retrace its path and it will come and stand here. Again, you start applying the magnetic field in the positive direction, then it will form a loop like this. Then this loop is what is called as hysteresis loop. Generally, hysteresis means lagging of something. Here, what is lagging? The magnetic induction is lagging behind the magnetizing field intensity. Guys, am I clear with this graph? This graph is very, very important. In the next chapter, we'll be learning about the application of this graph in transformers, in a device called as transformer.
So could you repeat the last point which you told about that lagging?
Yeah, hysteresis means lagging. So here, what is lagging? The magnetic induction will always be lagging behind the magnetizing field intensity. So that is why we call it as a hysteresis loop. Or some books refer to it as hysteresis curve also.
So I have a doubt.
Please tell me.
So here, after we provide H value, then after that only we'll get the B value. That's why it's lagging. So.
Yeah. Yes. Clear with this?
Yes, sir.
Okay. So OP is called as retentivity, I told you. Then what is OQ called as? OQ is called as coercivity. Okay. I'll explain what it is. So as the name suggests for OP, what do you mean by retentivity? Retentivity is a property of the ferromagnetic substance to retain its magnetization or retain its magnetism in spite of the removal of external magnetizing field. Am I right? So retentivity is a property of the ferromagnetic substance to retain its what? To retain its magnetism even on the removal of the external magnetizing field. Now, if I look at the point Q, what are going to be the coordinates of point Q? The coordinates of point Q will be minus h comma o. Sorry, minus h comma 0. Y coordinate is 0, it's on the x-axis. Right? Now, what does minus h comma 0 represent? So here 0 stands for y-axis and h stands for x-axis. Means it is a negative value of magnetizing field that we need to give. I repeat, it is a negative value of magnetizing field that we need to give to ensure that the material is completely demagnetized. I repeat, the negative magnetizing field that we need to give to completely demagnetize the iron material is called as coercivity.
I have a doubt.
Tell me.
Is it possible to give a negative value, sir, for H?
Negative value in the sense opposite direction. Here negative
Okay,
value in the sense I meant opposite direction. Opposite direction to the previous direction which you already gave. Clear?
Yes, sir.
Oh. Now, these are the definitions. Okay. So, if they give you a graph like this, okay, and if they give you a graph like this, okay, what is the difference between these two graphs? Here, if you observe, what can you say about the retentivity in the first graph and retentivity in the second graph? Similarly, what can you say about the coercivity in the first graph and coercivity in the second graph?
Both are higher in the second graph than the first graph.
Here, retentivity and coercivity is less. Then these kind of ions are used to make soft iron. They are used in solenoids, toroids, transformer, right? All these devices, the iron material which are used in all these devices should be ensured that they have low retentivity and low coercivity. So if that is the case, then what kind of substances need to be ensured that they have high retentivity and high coercivity? They are permanent magnets. Because we need to ensure that the permanent magnets do not lose their magnetic property under normal scenario. right? Lot of effort is needed to make it completely get demagnetized. You're able to understand. So sometimes what they will do is they'll give you this kind of a graph where this is B and this is H. Similarly, this is B and this is H, where they'll give you this kind of a graph and ask you which is used for making soft iron and which is used for making permanent magnets. Okay. Guys, am I clear?
Yes, sir.
Okay. So let's see the summary of this. So we have already discussed. Yeah, there's the only point we didn't see. If sometimes they'll ask you to draw the magnetic field lines through a diamagnetic, paramagnetic, or a ferromagnetic substance. If you draw the magnetic field lines through a diamagnetic substance, you can clearly observe that the magnetic field lines move away. The external magnetic field lines are mostly out of the material, right? So these light lines are there, no light colored lines. They are the magnetic field lines which are due to external field. So the external magnetic field lines are mostly out of the material, whereas in this case they are inside the material, and in this case also they are inside, except the fact that here it is going to be strong and here it will be weak. Clear, guys?
Yes, sir.
Now see. For permanent magnets, we need a material of high retentivity and high coercivity. For electromagnets, we need material of low retentivity and low coercivity. Similarly, there is something called as hysteresis laws that will take place. So if you observe, this is a complete process of, or a complete cycle of magnetization. The loop that you saw was a complete cycle of a magnetization and demagnetization effect. So what happens is, in this, if you pass an alternating current, right, there will be a cycle of magnetization and demagnetization, due to which heat will be lost in the, energy will be lost in the form of heat during this process. And that kind of a loss is what we call it as hysteresis loss. Okay. So this is all about the diamagnetic, paramagnetic, and the ferromagnetic substances. The last topic that is left in this chapter is Earth's magnetism, which will be completing tomorrow. Then I will start next chapter also. Okay, Earth's magnetism is very small. We'll do this tomorrow and we'll start the next chapter in tomorrow's class. So revise and come so that you understand things better. Okay. Any other doubt from today's class?
No doubt, sir. No doubt, sir.
Okay, then you can leave them.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.